Welcome, welcome, welcome. Okay, we are continuing our conversation of chemistry in this walk through physical science. And today we're going to look at why chemicals bond. Why is it that one molecule will form a bond with another? I'm sorry, one atom will form a bond with another. And what is the underlying, reasons, physical laws behind that? So the main idea is something called the Octet Rule, and we'll be talking about that today. Okay, so the Octet Rule, what does it say D? A, all right. The Octet Rule says that main group elements, the elements that are in the right and the left blocks of the periodic table, are most stable when they have 8 electrons in their valence shell. The valence shell is what we call the outermost shell of electrons. So we talked about how the atom has all these different layers of electrons. The outermost layer is the only layer that it uses for making bonds. And so however many electrons it has in inner layers, it doesn't matter for the bonding. Only the outermost layer matters for bonding. And so the Octet Rule says that these atoms are most stable when they have 8 electrons in their valence shell. It's called octet because oct is the prefix that means 8. So the Octet Rule is the rule of 8. Atoms want 8 electrons in their outermost shell. That's why noble gases don't react, because they want 8 electrons in their outermost shell, and they have 8 electrons in their outermost shell. And so noble gases don't really care to form a bond with anything else, because they don't need anything. They're self-sufficient. Okay. So something that only has 3 electrons in its outermost shell might say, "I feel so lonely. It's like I'm incomplete." Of course, atoms don't actually talk, but you know what I'm saying. So this might be looking for more electrons, right? If you look at a periodic table, just the main group elements, not the transition metals or the lanthanide and actinide, just the main group elements, and you look at their columns, we know that everything in column 1 has 1 electron, everything in column 2 has 2 electrons, 3 has 3, 4, 5, 6, 7, 8. So everything wants to be noble. Everything wants to be like a noble gas. These guys can pick up 1 more electron and be like a noble gas. These guys need to pick up 2. These guys need to pick up 3. And these guys need to either lose or gain 4. They're halfway there. They'll either get rid of the 4 they have and expose a full layer underneath, or they'll get 4 more and become a noble gas. Honestly, the ones in this column very rarely ionize and form ions. They mostly share electrons. These guys would like to get rid of the 3 they have and show a full layer underneath. These would like to get rid of the 2 they have and show a full layer underneath. And these would like to get rid of the 1 they have and show a full layer underneath. So that's why everything tends toward a noble gas, right? The Octet Rule could be stated as atoms tend to gain, lose, or share 1 or more of their valence electrons to achieve a filled outer electron shell. That would be one way of expressing the Octet Rule, that they tend to pick up electrons or give away electrons or share electrons, so that they're looking at 8, right? Another one might be, in chemical compounds, atoms tend to have the electron configuration of a noble gas. That's another way of expressing the Octet Rule. Okay, they tend to get an electron configuration that looks like a noble gas. Take a second, right? So in ionic bonding, it's a give and take relationship. The ions are formed when an atom that has extra electrons runs into an atom that needs more electrons. So the atom that has extra ones, that would like to get rid of a couple of electrons on the outermost shell so that it can show the full shell underneath, it gives an electron to the one that needs it. And then the one that gave them away is now positive because it's lost some negativity. And the one that received it is now negative because it's gained some negativity. And positives and negatives attract each other, the law of charges. And so that forms what we call an ionic bond. An ionic bond is an atom that has become negative and an atom that has become positive that are attracted to each other because of opposite charge. And they have those opposite charges because they have exchanged electrons. Okay? So one way of looking at this would be this little animation here. Sodium has an extra electron. It gives it away to chlorine, which would like one more electron. And the two become attracted to each other. So there goes sodium giving away its extra electron. Chlorine accepts it. Sodium becomes positive, and chlorine becomes negative. And then the positive and the negative are attracted to each other. Okay? And that's how we get table salt. It's another illustration with dogs. Dogs make everything easier to understand, right? One dog has one bone, the dog has another bone. The one dog steals the bone from the one that doesn't have any anymore, and now the one dog wants to hang out with the other one because he's got his bone, right? So this is a little silly illustration of ionic bonding. Okay, it's kind of cheesy animation though because the one dog is holding another bone, like, I don't know, through his head. I don't understand that, but it's okay, it works. So that's one illustration of ionic bonding, right? The other way of bonding is called covalent bonding. Take a second. The other method is covalent bonding. In covalent bonding, you have an atom that doesn't have enough electrons and another one that also doesn't have enough electrons. But rather than giving electrons away or receiving electrons, they share them. And then when they both get to look at shared electrons, they both feel like they're full. And so you have an atom that has 4 electrons and an atom that has 7 electrons. Well, the one that has 7 would like to have 1 more. And the one that has 4 would like to actually have 4 more. So what happens is the one that has 4 shares an electron with the one that has 7. And now the one that has 7 gets to look at one that it's sharing with the one that has 4, and then that one that has 4 does that 3 more times, and you wind up with the one that has 4 now looking at 8. And he feels like he's full, even though he's sharing half of those electrons, right? Sharing satisfies the octet rule as well, and that is called a covalent bond. Valent, thinking about the outermost layer, a valence layer of electrons, right? Co means like together. So they have blended their valence electrons. Covalent. They are sharing their electrons. Okay? So here's an example of that. These two atoms, both in their outermost layer, have 7 electrons. But if they can share their odd lone pair electron, then they both feel like they have 8, right? And then they're happy. So this is an example of covalent bonding. These could be chlorine molecules, because chlorine comes as a diatomic gas, Cl2 in nature, right? And so that's an example of that. Here's another example of that. The water molecule, oxygen has 6, hydrogen has 1. Hydrogen only needs 1 more because the first energy level is full at 2, not at 8. So it would like to share this electron with oxygen. And then by so doing, oxygen gets to look at this electron too, which means that it would see 1 more, and the hydrogen sees 1 more. And if oxygen does that twice, now oxygen is looking at 8 electrons, and hydrogen is looking at 2. And so they're happy with each other, right? Here's just some more examples of this. Phosphorus trichloride. Phosphorus comes with 5 electrons. And then it hooks up with 3 chlorines, and it shares an electron with each of the 3 chlorines. And now it's looking at 8. And the chlorine gets to share this electron with phosphorus, so it's looking at 8 as well. So it's happy. Water, we've already seen. Carbon dioxide is another example of that. Carbon comes with 4. Oxygen comes with 6. They share 2 pairs of electrons each. And now carbon looks at 8, and oxygen looks at 8. We have a double bond. Okay? So sharing electrons is called covalent bonding. And of course, dogs. So Here I have a dog. Each dog has one bone, and they wind up sharing their two bones, right? That's a covalent bond. All right. Take a second and write this down. So we just saw an example where carbon shared two pairs of electrons with oxygen. And so we don't have just a single pair of electrons, we have two pairs of electrons. That is called a double bond. And sometimes you'll even see examples where two atoms are sharing three pairs of electrons, in which case they have a triple bond. The more pairs of electrons that are shared, the more stable that bond is, the more energy that's invested in that bond, and the harder that bond would be to break. Okay? So single bonds share one pair of electrons, double bonds share two, triple bonds share three, and you can get some very high energy triple bonds that that exist in nature and are useful in all kinds of biological systems. Okay? Here's an example of a double bond, two oxygens, and each oxygen shares a pair of electrons, and so they are sharing 4 electrons, and they still all get to look at 8 electrons. They feel like they're full, but this is a double bond between 2 oxygen atoms. Okay, don't worry about that image so much. Here's another example of carbon double bonding with carbon, and they share 2 pairs of electrons. We can draw bonds as a single line for a single bond, as 2 lines for a double bond. So these 2 carbons are sharing 2 pairs of electrons each. Okay? And this is just what it looks like in space when they are drawn with where the electrons are. We'll get more into this in chemistry. Okay? And then triple bonds, again, showing stuff you don't need to worry about right now a whole lot, but just showing that there's one pair of electrons in the middle, and there's a pair of electrons up and down on the y-axis, and there's a pair of electrons left and right on the z-axis. So it's sharing 3 pairs of electrons. Okay, last one. The third kind of bond happens only in metals, and in that example we have nuclei that don't necessarily own any electrons. The atom travels with a certain number of electrons, but once it's joined with other metals, it just shares its electrons around. So a tin, sorry, I'm going to go differently. An iron atom might need 2 or 3 or 4 more electrons to share to fill up its valence level, but it doesn't ever try to be full itself. It just shares around the electrons that it has. So I jokingly kind of call these communist atoms because no one atom actually has enough. But if they all share, then they all feel good about their electrons, right? There's not any more electrons available, but I could give, if I'm an iron atom, and Nico's an iron atom, and Angela's an iron atom, I might give my electrons to Angela, and she's like, oh, I'm happy. And then I pass them off to Nico, and then he's happy, and he passes them back to me, and I'm happy. And we just pass these around. And at any one given time, nobody actually is full. But the electrons are all just moving around, and at some instant, some atom is like, I've got 8. Oh, no, no, I don't. And they just get all moved around. So you have this sea of electrons that are flowing around a couple of nuclei that are positively charged. And so their individual deficit or surplus doesn't really matter. And metals don't try to satisfy the octet rule. They're just constantly sharing their electrons. Okay? So this is just some images of that. You have positively charged nuclei and electrons just zipping around through this matrix. And this would be like the picture with dogs, right? We all have our bone, and we come with our bone, and then we want more bones. So we just keep sharing our bones around. And then we feel good about our bones because I'm sharing and you're sharing, and hey, I can take a bite of yours, and you can take a bite of mine, and it's all just lovely, right? So that's what we're getting to here with metallic bonds. And this only happens with metals. And this is why metals conduct electricity so well. Because if you pour electrons into one side of the metal, all the electrons just move around. And the electrons come flying off the other end. That's why metals conduct electricity. It's also why they conduct heat. And a lot of their unique characteristics are because of this. Okay, that is it. Are there any questions about the three kinds of bonds?